Hi, welcome back. In this video, we're going to do a short linear algebra proof. In this proof, we're going to prove the statement, if A is an invertible matrix, then A transpose inverse equals A inverse transpose. So first, let's try to figure out what that equation says that we're trying to prove. On the left side, we have the inverse of some matrix. On the right side, we have some other matrix. Okay, so what we're trying to prove is that if we multiply together A transpose times that other matrix, A inverse transpose, we will get the identity matrix. And that will show that A transpose is the inverse of A inverse transpose. Okay, and what are we going to use to do this proof? There's a theorem in chapter 2, theorem 2.6, part 4 of that theorem says, when you multiply two matrices together and then you take the transpose of that product, that's the same as first taking the transposes of the two matrices individually and multiplying those together, but in the reverse order. So AB transpose, or the transpose of A times B, is the same as the transpose of B times the transpose of A. We're going to use that in our proof. All right, so we're going to start the proof. Always we start with the assumptions. Well, the only assumption here is that A is an invertible matrix. So let's give that invertible matrix a name. Let's call it A. Let A be an invertible matrix. So that it means it can be any invertible matrix. It's n by n. Now let's start with the left side of the equation we're trying to prove. The left side says the transpose of A times the transpose of A inverse, okay? And now what we're going to do is use the theorem, part 4 of theorem 2.6, and that theorem says we can reverse the order of the two matrices A and A inverse, multiply those together, and take the transpose of that result. So in other words, I'm going to write A inverse times A transpose. And now notice what's inside my parentheses. So this, I have to justify my step. So I have to write down, this is by theorem 2.6.4. And now what's inside my parentheses is the n by n identity matrix, In. So A inverse A transpose is really In transpose. And that's by definition of inverses. And now, what's the transpose of the identity matrix? So remember, the identity matrix is a diagonal matrix. It just has ones on the diagonal and zeros elsewhere. So if you swap the rows, swap the columns, they're equal. In other words, the identity matrix is symmetric. So we can say In transpose is the same as In, and that's because the n by n identity matrix is symmetric. So now we've proven that A transpose times A inverse transpose gives us the identity matrix. Well, that means those two matrices are inverses of each other. In particular, A transpose, the inverse of A transpose is A inverse transpose, what we were trying to prove. So that's the end of that proof, and I think you know where I'll see you